Now let's look at problem 14 in 2022 AIME 1. So this problem says the following thing. So it defines an important concept called the splitting line of the triangle ABC. So it means the following thing. Say this is triangle ABC, and let's pick up a point P. And then we say this is a splitting line that passes through point P. Say, for instance, this one, in the sense that the two separated polygons by the splitting line has the equal perimeter. Okay, so basically it says that the sum of these three side lengths is equal to the perimeter of this polygon. And we observe that these two polygons share a common side. So that is essentially the splitting line, right? So we could remove their shared sides. So this is essentially saying that the length of the yellow part is equal to the length of the green part. So that is what a splitting line means in this problem. Okay? And then this problem says that we are particularly interested in the following two splitting lines. So one passes through the midpoint of one side called AB, and the other one passes through another midpoint of the other side called AC. So now let's try to have a deeper understanding about how this splitting line looks like when it passes through the midpoint of one side of the triangle. So let's say this is the triangle ABC, and M is the midpoint of AB. So now let's try to draw the splitting line that passes through this point. So when you attempt to draw the splitting line, so you'll encounter the following issue. So it's not quite clear yet whether it will cross BC or it will cross AC. It's not quite clear, right? So let's see what it really depends on. So for example, suppose now for the illustration purpose, and also to help us to build up a good intuition, let's say this is the splitting line that passes through BC. So then what it tells us. So here's what we know. So basically, these are the yellow lines, and here are the green ones. So we know that these two colors polylines should be with the equal length, right? And in addition to that, because the problem tells us that M is the midpoint of AB, so basically AM is equal to BM. So we could just delete these two. So it essentially tells us that, so in this reduced graph, the length of the yellow part is equal to the length of the green part. So what that is exactly means? That exactly means that, so for two sides of the triangle BC and CA, so basically you could treat them to be a line that is folded at point C, right? So if you unfold these two lines and make it flat, so it's like this. So here's BC, and you unfold AC and make it flat to make it here, right? So this cutting point, let me call it X. This is essentially the midpoint of BA. Okay, so actually this is a very important observation that helps us to determine the location of point X. So here I define point X to be the point that the splitting line that it passes through point M meets the triangle at. Okay? All right. So because we know point X is the midpoint of the polyline BCA, so actually we could get a good idea about whether it is located on BC or CA. So we know that if BC is longer than CA, then X should be on BC. Otherwise, X should be on CA, right? Okay. And analogously, let's use the same intuition to understand the splitting line that passes through another midpoint, that is the midpoint of AC. Let me redraw this triangle ABC. Recall that N is the midpoint of AC. So let me use notation Y to denote the point that the splitting line that passes through the point N meets this triangle at. So we know that if we draw the following polyline, that is AB and BC. So basically we just to try to unfold AB and rotate it to make it flat on the same line with BC, right? So for this polyline, we know that Y is essentially its midpoint. So also we get the same intuition that if BC is longer than AB, then Y should be on BC. Otherwise, Y should be on AB. Okay? All right. So after having this good intuition about the locations of points X and Y, so now let's try to solve this problem. So because it's very important to know that whether X and Y are on the bottom side, BC, or they are on either AB or AC. So we have to do the casework analysis for this problem, okay? So this problem tells us the length of BC, but it doesn't tell us anything about AB and AC. So without loss of generality, we could simply assume that AB is less than or equal to AC, okay? All right. And also to lighten our notation, let me simply denote by A, the length of BC, and small b, the length of AC, and small c, the length of AB, okay? So we have to discuss the following three different cases. So as I said, because without loss of generality, we assume C is lower than or equal to B. So we could have three different cases. For the first case, let's assume that A has the smallest length. For the second case, we look at the scenario that A is in the middle. For the third case, we assume that A is the longest one. Okay. So now let's discuss each of these three cases respectively. So let's first look at the first case. That A has the shortest length. Okay. So maybe we could draw the graph roughly. No, this is not pretty good. So we want it to be short. Yeah, this seems to be good. All right. So for this case, let me make the point M. So let's find out the location of X. So because here we know that for the polyline BCA, X is its middle point, right? And we know that A is less than or equal to B. So it tells us that X must be on segment AC. Okay? So X might be somewhere here. All right. So now actually I want to draw the following auxiliary line. So let's look at line AC. So now I would like to unfold BC to make B to fall onto line AC. So let's rotate BC around point C and make it with the same line as BC. So say B goes to here. Okay, so let me call this point as B prime. So basically here we assume that these two are with the equal length. Okay, so by doing this rotation, then we know that X is the midpoint of AB prime. Okay. All right. So next, let's look at another splitting line that passes through point N. That is the midpoint of AC. Okay. So we know that the point Y should be the midpoint of the polyline AB and BC. So because we know that AB is longer than BC, so we could do the similar operation. Let's extend AB to the point, let me call it C prime, such that BC prime is equal to BC. So by doing this operation, then we know that on the line AC prime, so Y should be its midpoint. All right. So now let's do some further analysis. So let's first look at line MX. Okay. So here's what we know. Because M is the midpoint of AB and X is the midpoint of segment AB prime. So let's look at the triangle ABB prime. So let me extract it here and draw it to the left. So this is A, B, and B prime. So we know M is the midpoint of AB and X is the midpoint of AB prime. So it is obvious, starting from the side angle side, that triangle AMX is similar to triangle ABB prime. And that further implies that MX is parallel to BB prime. Okay. And analogously, if you apply the similar argument onto another triangle, ACC prime, because N is the midpoint of AC and Y is the midpoint of AC prime, so we know that YN is also parallel to CC prime. Okay. All right. So actually, this parallel observation is very important in the sense that recall that this problem tells us that the two splitting lines that are MX and NY, they cross and they form an angle that is equal to 30 degrees, right? So by having such parallel properties, it essentially tells us the following equivalent fact, that the angle formed between BB prime and CC prime is equal to 30 degrees. So now actually you only need to analyze the positions of BB prime and CC prime. We no longer have to look at MX and BY and NY anymore. Okay? All right. So what we could do next? Because we have to analyze BB prime, let's connect BB prime, and also let's connect CC prime. So what properties do we have? Here's the thing. On this graph, so we observe that because BC prime is equal to BC, so this is a isosceles triangle, right? Then we know that these two angles are congruent. Okay, so the sum of these two angles should be equal to here. This is the angle B, right? So it tells us that this, let me call it angle cross, is equal to 1/2 of the degree measure of angle B. And analogously, if you look at another triangle BCB prime, so we know that these two are congruent. So the sum of these two is equal to here, angle C. So that implies that the degree measure of each, let me call it a circle angle, is equal to 1/2 of the degree measure of angle C. All right. So now let's look at the angle that is formed by these two blue lines, BB prime and CC prime. So let's look at this one. Okay, let me call it theta. So how theta could be expressed in terms of angle X and angle O. So here's the thing, right? Now you look at this triangle here, the green one. So we know that theta is equal to this one plus this one. So recall that X is equal to 1/2 of B and O is equal to 1/2 of C. So this is equal to this one. And recall that angle B plus angle C is equal to 180 minus angle A. So when it is divided by 2 is equal to 90 minus half angle of A. Okay? All right. So recall that this problem tells us that the angle formed by these two lines, BB prime and CC prime, is 30 degrees. So actually, there are two ways to understand 30 degrees. So one is to say that theta is exactly equal to 30. And another way to interpret it is another possibility that it's essentially the supplement of 30. So that could be 180 minus 30 is 150. So when we say two lines cross each other and forms an angle of 30, it tells us two possible solutions for theta, that it could be equal to 30 or its supplement is 150. But for this case, because we know that theta is less than 90 degrees, so it's 90 minus 8/2. So this implies that we can only have theta is equal to 30 in this case. So let's plug it into this equation. It further implies that angle A is equal to 120. Okay? All right. So now let's check whether this is feasible for this case. So in triangle ABC, we know that angle A is equal to 120 degrees. So that implies that this is an obtuse triangle, right? So for an obtuse triangle, because angle A is obtuse, so that implies that its corresponding side that has the length small a, right? So that should be longest. But that actually is a contradiction with our condition for the first case. Because recall that in this case, we assume that A is the shortest. But because angle A is 120, that implies small a is the longest. So we get a contradiction. So that implies that this case is infeasible. Okay? All right. So then let's look at the second case, that for the three side lengths A, B, and C, and we assume A is in the middle. It's between C and B. Okay? All right, so first let's try to sketch the graph. Yeah, it should be something like this. Okay. All right, so let me first draw the midpoint of ABM. And recall that X is the second point of the splitting line that crosses M that would meet the triangle ABC at, right? So because recall that X is the midpoint of the polyline AC and CB. And in this case, we assume that B is longer than A. So basically that means that X should be on AC, right? And by using the similar trick as what we did for the previous case, so now what we're gonna do is to extend AC to a point called B prime, such that BC and C prime are with the equal length. So by doing such an operation, then we know that X is the midpoint of AB prime. And then let's look at another splitting line in Y. So N is the midpoint of AC. So we know that Y is the midpoint of the polyline ABBC. So for this case, we assume small a is bigger than or equal to small c. So that tells us that point Y is on segment BC. So in this case, we will draw the auxiliary line in the following way. So we will extend CB to a point, let me call it A prime, such that BA is equal to BA prime. Okay? All right. So by drawing this auxiliary line, then we know that Y is the midpoint of of C A prime. Okay. All right. So next, let's try to find out the parallel property. So first, let's look at triangle ABB prime. For triangle ABB prime, so because M and X are the midpoints of AB and AB prime respectively, so that tells us that MX is parallel to BB prime. Analogously, for the splitting line in Y, because N is the midpoint of AC and Y is the midpoint of A prime C. So that tells us that in Y should be parallel to A prime. Okay. So this problem basically tells us that MX and in Y, they cross each other to form an angle whose degree measures 30. So by having such two parallel properties, it tells us that the angle formed by lines BB prime and AA prime should be equal to 30, right? So let me draw BB prime and AA prime. Okay. All right. So, but unlike the previous case, that when we draw those two lines, so they cross each other, so they form an angle. But here, these two blue lines actually do not meet each other. So what we have to do is to do the following trick. So let's shift the line AA prime and let it pass through point B. So basically, let me draw this parallel line that passes through B. Okay, and let's analyze this angle. So what this angle is about? Here's the thing. First, let's look at the green triangle, ABA prime. Because this is isosceles, so we know that these two are congruent. And they should be equal to the half of B. And then let's look at the bottom right triangle, the yellow one, because BC is equal to B prime C. So let me denote as circle angle. So this is C, so they should be equal to a half of C. Okay. All right. So then let's look at these two parallel lines here and here. Because they are parallel, so we know this is cross and this is also equal to cross. Okay. So what about the angle formed by these two blue lines? So we can observe that it is equal to the cross one plus the circle one. Okay. So let me call this as theta. So theta is equal to cross plus circle. So is equal to 1/2 of B plus C. So by doing the same thing as we did for the first case, is simply equal to 90 minus 1/2 of A. So recall that we assume these two lines, BB prime, A prime, cross each other to form an angle that is with degree measure 30. So that means theta is equal to either 30 or its supplement is 150. But since theta is less than 90, so this requires theta to be equal to 30. So this further implies that A must be equal to 120. So we get the same result as the first case. But again here, because we get the same result, so we got the same contradiction. Why? It is because A is obtuse. So for triangle ABC, so the length of the side that is opposite to angle A is the longest. So that implies that small a should be largest among ABC. But this is a contradiction with the condition given in this case. So we got a contradiction for the second case. It's not good. All right. So it seems that the only hope to get some good result is to get something from the third case, right? So now let's analyze the third case. In this case, we assume that A is the largest one. So let's see whether we could get some exciting result from the third case. So this is what we attempt to analyze. Yeah, again, let's first draw the graph. Yeah. So A, B, and C. Okay. All right. So first, let's start from the splitting line that passes through the midpoint of AB, that is M, right? So in this case, because small a is bigger than small b, so we'll do the following operation. So let's extend BC to point A prime such that AC is equal to A prime C. Okay. So then it tells us that X should be the midpoint of BA prime. Okay. All right. So now let's look at the triangle ABA prime. Because M is the midpoint of BA and X is the midpoint of BA prime, so that implies that MX should be a parallel to AA prime. And then let's look at the second splitting line that passes through the midpoint of segment AC. That is N, right? So let's do the similar thing as what we did on the right side, colored in yellow. So we'll extend CB to a point called, oh, we already have A prime, so let me call it A double prime, okay? Such that AB is equal to A double prime B. So by doing this operation, then we know that point Y should be the midpoint of segment A double prime C. Because Y is the midpoint of this segment and N is the midpoint of AC, then we know that NY should be parallel to A double prime. Okay? All right. So analogous to what we did for the previous two cases. So by analyzing the angle formed by MX and NY, because we have these two parallel properties, so it is equivalent for us to analyze the angle formed by AA prime and A double prime. Okay. So first, let's look at the left, the green triangle. It is isosceles. So let me use cross to denote these two angles. Then we know it is equal to 1/2 of B. And for the right yellow triangle, it's isosceles. Let me use circle to denote these two angles. So it should be equal to 1/2 of C. So what is the angle formed by these two blue lines? This one, let me call it theta. So it is equal to B over 2 plus C over 2 plus here, this is angle A. So what that is equal to? Let's do the following manipulation. So the first one, the sum of three angles equal to 180 divided by 2 is 90. So this is the value of theta. Recall that the angle formed between these two blue lines is 30. So it tells us theta is equal to 30, or it supplement 150. In this case, theta is obtuse, so theta has to be equal to 150. So that implies that A is equal to 120. So in this case, actually, it's okay to let A be equal to 120. Why? It is because in this case, recall that we assume that small a is the largest, right? So now we get a consistent result. So this is good. All right. So then let's continue to do the rest of the analysis of this problem. So recall that this problem tells us the length of BC. Let me check what that is equal to. Oh, 219. And also it says that AB and AC are integers. And it asks us to find out the length of the AB and AC. So what formula could help us to build up the connection of the length of the three sides of the triangle by knowing that A is equal to 120? So we have to apply the law of cosine, okay? So we know that small a square, so that is 219 square is equal to b square plus c square minus 2bc cosine a. So a is 120, then cosine a is equal to negative 1/2. So this is equal to this one. All right. So now the problem boils down to the following one. So we have to find out the integer solutions for B and C that satisfy this quadratic equation. Okay. All right. So for the rest of the analysis, because we are restricted to integer solutions for B and C, so we know that this is not the typical algebraic problem, but this is a number theory problem. So we have to use some number theory skills to find out the solutions for B and C. Okay, so let's do it. So for this equation, actually, we are not worried too much about having the square term, but we definitely don't like the cross term. How we get rid of the cross term? So this is perhaps what we could try to do. So let's try to multiply both sides of the equation by 4. Then we get the following equivalent one. So 4b squared plus 4c squared plus 4bc is equal to 219 times 2 is 438 square. Yes. So the reason that we write in such a form is that, so now let me do the following analysis. You can see that we are able to write the left-hand side as the sum of some perfect squares up to some the coefficients. So that will allow us to absorb the cross term into one perfect square. Let's do the following thing. So let me rewrite the left-hand side as 2c plus b squared. So you can see that basically 4bc, the cross term is absorbed into this perfect square, right? And the leftover term is 3b squared. That is equal to 438 squared. Okay. So now you can see the left-hand side has no cross term anymore. It's just sum of some squares up to some constant 3. That's it, right? So let's solve this problem. So for this problem, actually, for the first term, we have 2c plus b. This is very, very ugly. We don't like it. So why don't we just do the change of variable to simplify the notation? So let me denote 2c plus b as a new variable. Let me call it just a d. Okay. So we need to solve the following equation. Right? So this is pretty elegant. So is there any restriction on b? Yes. So recall that in this case, we assume that c is less than or equal to b. Right? So here we assume d is equal to 2c plus b. So what is the relationship between b and d? So first, we know that d must be bigger than or equal to b plus 2, because the smallest value for c must be 1, right? So what is the upper bound of D? Because C is upper bounded by B, so 2C plus B is less than or equal to 3B. So D is upper bounded by 3B. So basically, this is the domain for D. Okay. So now let's try to solve this equation that is subject to the constraint given in the green box. So actually, the starting point here is the coefficient 3 on the left-hand side. So let's see how that will help us to find out more structures of B and D. So why don't we just do the modular arithmetic analysis to see what we could get? Because the left-hand side has coefficient 3, so it motivates us to choose the modulus 3. So let's do modulo 3 on both sides of the equation. Then the left-hand side is congruent to D squared. What about the right-hand side? So right-hand side is a multiple of 3. So this tells us that D squared should be congruent to 0 modulo 3. Because D squared is a multiple of 3, it implies that D should be a multiple of 3. Okay? All right. So since D is a multiple of 3, why don't we write D as 3 times a multiplier? Let me call it Q. So let's plug D is equal to 3Q into the green equation above. So we get is equal to 9Q squared plus 3B squared is equal to 438 squared. Okay? All right. So what do we observe now? For 438, we know we have a multiple of 3. It could be written as 3 times 1, 4, 6. So it's equal to 9 times 1, 4, 6 squared. Let's look at this equation. So the right-hand side is a multiple of 9. The first term on the left-hand side is a multiple of 9. So it requires the second term on the left-hand side, 3B squared, to be a multiple of 9. So that implies that B squared has to be a multiple of 3. So that further implies that B has to be a multiple of 3. Given this fact, so we can write B as 3 times a multiplier. Let me denote it as P. So let's plug it into the equation above. And we could divide 9 on both sides of the equation. So we get the following equation. So Q squared plus 3P squared is equal to 146 squared. Okay? So yeah, let me highlight these conditions in yellow here. All right. So now let's solve this equation. And don't forget the range for D. So because here we write D and B as multiples of Q and P respectively, so the relationship for P and Q is as follows. So Q is less than or equal to 3P, is bigger than or equal to P plus 2. Yeah. So next, let's solve for the equation with Q and P. How to solve it? Well, so we definitely don't want to try all numbers from 1 up to 146. There are too many numbers. We don't want to waste our time, right? It's not good. So actually, what we could do first is to first determine the range for Q. So let's try to first narrow down the possible range for Q. Okay. So let's determine the upper bound and the lower bound of Q. So first, let's find out what is the maximum possible value for Q. So let me call upper bound of Q. So for Q squared plus 3P squared we know that it's greater than or equal to the following thing. So let's look at the green box. So Q is less than or equal to 3P. So that implies P is greater than or equal to Q over 3. Okay. So this could be written as this one. And also recall that Q squared plus 3P squared is 146 squared. So this tells us that this is bounded by this one. So this implies that Q is less than or equal to 73 square root of 3. So now we just need to roughly estimate the upper bound of square root of 3. We know square root of 3 is equal to 1.7 something. So it is bounded by 1.8. So by doing some simple computation, this number is equal to 131.4. So Q is less than this number. And because we know Q is an integer, so this further implies that Q is upper bounded by 131. So this is the upper bound of Q. And second, let's establish a lower bound of Q. So for this one, we know that this is the strict inequality. So recall that Q is equal to P plus plus something, right? Q is bigger than or equal to P plus 2. So it's obvious that P is less than Q. Okay. So this tells us that this is bigger than this number. Okay. So this implies Q is bigger than 73. Because Q is an integer, so the lower bound of Q is 74. So now we have established the upper bound and the lower bound for Q. So now we know that the possible range for Q is that it is between 74 and 133. So actually it's not too bad because we have narrowed down our search for Q. We don't have to try all numbers below 146, right? But the ugly thing is, so this is still a very big range. So there are lots of numbers in this range. So of course we should not try each of them by hand. It's not good. So is there any way to further narrow down our search and to delete some numbers in this range that cannot be possible without doing some specific computation? Yes. So again, so let's go back to the green equation here. So let me copy paste this equation here. So let's try to do some additional modular arithmetic analysis and see that, so what kind of the Q's in this blue range that is not feasible. So which modulus we should choose and we should apply on this equation. So let's do some trial. First, because the left-hand side has coefficient 3, so we could definitely do modulo 3, but actually I want to be more aggressive. So why don't we just try modulo 9? The intuition is because so every term is a perfect square, right? So basically we could try modulo 9 and see what we could get. So by doing modulo 9, for right-hand side, we know that so 146 is congruent to the sum of the 3 digits, 1 plus 4 plus 6. So 11 is congruent to 2. So right-hand side is congruent to 2 square is equal to 4. Okay. What about 3p square? So we know that, so modulo 9 we only need to, for 3p squared, when we compute its congruent number modulo 9, so it is equivalent for us to compute the congruent number of p squared modulo 3, right? Because we have the coefficient 3. So for perfect square modulo 3, we know that, so it can only be congruent to 0 or 1. It cannot be congruent to 2, right? So because p squared is congruent to 0 or 1 modulo 3, so when it is multiplied by 3, so we essentially know that, so for 3p squared modulo 9, so it must be congruent to either 0 or 3. Now let me write it here. And the right-hand side is congruent to 4. So how to make this equation to hold modulo 9? So that essentially requires q squared to be congruent to 1 or 4 modulo 9. So how can it be congruent to these two numbers modulo 9? Well, so that essentially tells us that modulo 9, q should be congruent to 1, 2, 7, or 8. Okay. So this is modulo 9. So basically it tells us that, so q cannot have an arbitrary remainder when it is divided by 9, right? So that basically would help us to eliminate lots of numbers that fall into the blue range on the top of this screen. Okay. All right. So it seems that the result is very good. It's remarkable. So actually, this is not the end, because we can easily see that. So because here we still have 4 possible congruent numbers modulo 9. So it tells us that there are still lots of numbers in this blue range. So maybe next we should try some other modulus and see whether we could get a similar result that will further help us to delete some additional numbers. So after trying 9, because 9 follows from 3 squared, so the next number we may try is 5, because 3. So after trying 3 squared, this from 3. So the next one, the prime is 5. Let's try 5. So for this green equation, for the right-hand side, we know modulo 5, this is congruent to 6 squared is congruent to 1. What about 3p squared? So we know that for a perfect square, modulo 5, it can only be congruent to 0, 1, or negative 1. So when it's multiplied with 3, it is congruent to 0, 3, or negative 3. Okay? All right. So that implies that to make this equation holds, we require q squared to be congruent to 1, 3, or negative 1. And in addition, we know that for a perfect square, modulo 5, it can only be congruent to 1, negative 1, or 0. So what kind of the congruent numbers that could meet both of these two conditions? So that can only be 1 or negative 1, right? So what kind of the remainders q could have when it's divided by 5, such that q squared is congruent to one of these two numbers? So we know that q could be congruent to 1, 2, 3, 4 modulo 5. So equivalently, this is essentially to say that modulo 5, so we simply require that q cannot be a multiple of 5. So that's the condition we get by doing the modulo 5. Okay. So it seems that this condition will not help us to eliminate too many numbers, right? So probably we have to continue to do more analysis by trying another modulus. So the next modulus that we may try would be 7. Let's see what's going on. So recall that q squared is this number minus this number. So for 146 modulo 7, it is congruent to -1. So -1 squared is simply equal to 1 minus 3. So what about the possible congruent numbers of a perfect square modulo 7? So we can easily find out that. So the only possible congruent numbers of a perfect square modulo 7 could be 0, 1, something else. Let me see, 1. So P2 squared is the 4. Well, this number 0, 1, 4, 2, right? Yeah. So let me put it down in here. So let me put down the congruent numbers of P and P squared. So P is 0 plus -1, 2, 3. So 0, 1, 4, 2. Yeah. So if 0 is congruent to 1, it is 1 is congruent to 1 minus 3 is -2. So -2 is 5. 1 minus -3 times 4 is 12. So that would be 3. And the last one, -3 times 6, it should be 2. Okay. So here are the possible congruent numbers for q squared. And because for q squared itself, so following from the table on the right, we know that it's possible congruent numbers modulo 7 could be 0, 1, 4, 2. So basically, in order to satisfy both of these conditions, so the only possible congruent numbers here, we can see that it can only be 1 or 2. Okay, they are here. So now let's find out the possible remainders of q divided by 7 such that q squared is congruent to either 1 or 2. So we know q could be equal to 1. It could be congruent to 1, 3, 4, and 6. Okay. All right. So actually, this seems to be good, right? Because modulo 7, we could have 7 in total different remainders. So here we can only admit 4. So we have to exclude 3. So it's not too bad. All right. So after finding out the possible remainders when q is divided by 3 different numbers, 7, 5, and 9. So it seems that we're able to exclude lots of numbers in this blue range, right? So let's see what numbers survive after doing this 3 modulo analysis. So in this video, actually, I will not just waste your time to see which numbers could survive. Let me just put down all surviving numbers here, okay? Wow, we still have lots of numbers that are remaining here, but it's okay. It's not too many, right? So what we need to do next, because we don't have too many numbers left over, so let's do just do the basic computation and try each of them and see which one would basically the solution of the of this equation. Okay. All right, let me put it here. So the way to solve it is as follows. So we write it in the following form. And let's apply this factoring formula. Okay. So then basically we can easily compute out the right-hand side. But for each of the Q listed in this list, so the trick is you should not attempt to basically compute each factor on the right-hand side and multiply them together to get a very big number. That's not the point. So the trick is here. So after getting each factor of the right-hand side, so we know that, so we must have the factor 3 either in the first term or the second term. So let's just get rid of 3. And for the rest terms, in order to be the solution to this equation, it must be a perfect square. So then we'll do the prime factorization of every term on the right-hand side and to see that whether every prime factor appears for the even number of times. If this is the case, then this is the solution to this equation. Otherwise, this is not a solution to this equation. So let me do some illustration for you here. So for example, suppose I want to try 74. I want to see whether 74 is a solution or not. So let's try the right-hand side. So the first term is equal to this one. The second term is equal to this one. So you don't necessarily have to compute out the product. Just do the prime factorization. So you can easily observe that for the first number 220, it has a prime factor 11, right? So 11 appears with multiplicity just 1. But the second term, 72, has no 11. So it means that 11 appears for just one single number of times. So it implies that there will be no way for you to get the p square here. Otherwise, so 11 must appear for at least 2 times, right? So basically, here you can easily conclude that so 74 is not a solution. So you could stop trying 74 and you move on forward to the next number, 83. Okay. All right. So basically, I'm following this quick way, this trick to try all these numbers. Then you could eventually find out that the only feasible Q is this one, 97. Let's see why it works. So the first term is seems to be equal to this one. The second term is oh, it's my bad. Yeah, this is correct. So let's see why it could be written as 3p squared. So we need to first take out 3. And then the first term is 81. The second term is 49. Oh, so now it is so obvious. 81 is 9 squared. 49 is 7 squared. So it's equal to 9 times 7 squared. So 3 times 63 squared. So we get p is equal to 63. So that is really awesome, right? So now we have found out the values for p is 63. And recall that here q is equal to 97. So now let's plug it back to b and d here. So let me see in which step we change the variable. Oh, here we set b equal to 3p, d is equal to 3q, right? And recall that we define d to be equal to 2C plus B. So now we can compute out B and C. So B is equal to 3P is equal to 189. And 2C plus B is equal to D is equal to 3Q is equal to 291. So plugging B into the second equation, we could get C to be equal to 51. All right. So recall that this problem asks us to report the perimeter of the triangle. So we simply compute A plus B plus C. Recall that the problem tells us A is equal to 219, B is 189, C is 51. Summing them up, we get the number 459. So that is the answer to this question.